Okay, number 14. We have a function to find a piecewise function of x squared for x less than or equal to 2, and then 8 minus 2x for x greater than 2. Alright, so we're approaching a value of 2. And we want to see whether or not we can find the limit from the left and from the right. That means that from the left means that we're going to use all values of x less than 2. We're going to approach 2 on the left as we were to look on it on a graph, let's say. So for x less than 2, which one of these two functions are we going to use for f? And I'm going to say, alright, well, if I'm of any value less than 2, and it could be 1.99999, that's still a value which is less than 2, so I'm going to use the top function. So the limit as x goes to 2 on the left of f of x is the same as the limit as we approach 2 on the left of x squared. But x squared, we can just use direct substitution for all limits, right? Because it's just a polynomial function. So that means that we can use direct substitution on this, and we know that the limit as x goes to negative 2, so for example here, if I were to say find the limit as x goes to 2 of x squared, you would say, hey, that's 4. I can use direct substitution. I know that all polynomials are continuous everywhere, so for all x values. So if this limit is defined, one of the things about that is that the limit is equal as you approach both from the left and from the right. So we know that this means that the limit as x goes to 2 on the left of x squared is equal to the limit as x goes to 2 on the right of x squared, which is equal to 4, right? So if in order for a limit to be defined, it has to approach the same value on the left and right. And so this fact is what I'm using here, right? That the limit as x goes to 2 on the left of x squared is 4. So if that is true, right, now let's do it from the right. But from the right, our piecewise function f of x looks instead like 8 minus 2x. If it was 2.0001, it's still a value greater than 2, and we are going to say, I'm going to use the bottom function. So the limit as x goes to 2 on the right of f of x is going to be the same as the limit as x goes to 2 on the right of 8 minus 2x. And that is equal to 8 minus 4, or 4, because we know that we could use direct substitution on this, right? And in the same way as before, right? We couldn't use direct substitution on f, right? Because we don't know which of the two functions to use, but we can use direct substitution on this quantity at least to figure out what the limit is as it approaches from either the left or the right. So the limit as we approach on the left and the right of f of x is equal to the same value. So if that's true, then the limit is defined, and it's equal to whatever value that it approaches on the left and the right, which is 4 in both cases, for x less than 2 and for x greater than 2. So the limit's defined, and it is equal to 4. Contrast this with number 15. So in number 15, again, we have the same exact situation, just with different functions on the top and the bottom. If we want to find the limit as x goes to 2 on the left of f of x, it'll be the same as finding the limit as x goes to 2 of whatever this top function is. So the limit as x goes to 2 on the left of negative 2 we know is equal to negative 4, because we can use direct substitution on this thing. The limit as x goes to 2 on the right of f of x, well, for any value that is greater than 2, we are going to use this bottom function. So this bottom function is x squared minus 4x plus 1. So the limit as x goes to 2 on the right of x squared minus 4x plus 1, we can use direct substitution on that, and we figure out that it's equal to negative 3. after we do our direct substitution. So on the left, it approaches a value of 4 as x goes to 2. And as x goes to 2 on the right, it approaches a value of -3. A lot of people stopped here, but you have to actually go one step further and say that the limit does not exist because it doesn't approach the same value. So we would say that the limit as x goes to 2 of f of x, we would say does not exist. Because I couldn't tell you which of these two values is more important to use, right? The limit exists as you approach from the left and from the right, but if they aren't equal in both cases, then we can't say that one value is better than the other, so we would say that the limit does not exist. Okay, so that's number 15. Number 16 was a little bit harder, and I turned it into a extra credit question. So if anyone got anywhere close to this, I made it into extra credit, and I will put it into a separate video. Okay, so number 17. Now, a lot of people had trouble with 17 through 19, determining the continuity of a function. And it's really not that hard. To determine the continuity of the function, first you have to determine where it isn't continuous, where there are discontinuities. And in order to determine where it is not continuous, you just have to say where the function is undefined or the limit doesn't exist. So we know here that this is a rational function. The numerator is x minus 6. The denominator is x squared minus 36. And this function is not continuous wherever the denominator is equal to 0. The denominator is equal to 0 at values of x plus 6 and x minus 6. And you can see that from factoring it. So there are discontinuities at values of x plus 6 and x minus 6. There is, so we say that this function is not defined at values of x equal to plus or minus 6. So therefore it's discontinuous at those points. One of them is removable because we have a factor of, I'm sorry about that, hold on. We have a factor of x minus 6 on both the numerator and the denominator. So at a value of x plus 6, the discontinuity is removable, meaning that the limit exists on both sides and it's equal to 1 over 12, right? If we do direct substitution into this for a value of x equal to 6. So there's a removable discontinuity at x equal to 6. There's a non-removable discontinuity at x equal to negative 6, and it's continuous everywhere else. Everywhere else, note, is let's say negative infinity to negative 6. It's continuous between negative 6 and 6, and it's continuous between 6 and positive infinity. Notice that these are open intervals, so I don't include values here, right? And actually, it's a removable discontinuity, so we could say, include 6 there. Okay, so number 18, it's the same thing, but we have to factor out the numerator. Some people had trouble factoring out the numerator, and if you do, we just need to review the pre-calc review sheet and review factoring. So 3x squared minus x minus 2 factors into x minus 1 times 3x plus 2. And one of the other things that you could do is, hey, I know that one of the factors is probably going to be x minus 1, so you could put that in and see whether or not you can figure out what the other factor would be to get 3x squared minus x minus 2. And otherwise, if you couldn't do that, then it's not going to cancel anyway, and it doesn't really matter, right? So, but you can, and it factors into x minus 1 times the quantity of 3x plus 2. This factor of x minus 1 cancels between the numerator and the denominator, so we get 3x plus 2 as what this function is equivalent to. So we would say that there is a removable discontinuity at x equal to 1, and it's continuous everywhere else. And when we say everywhere else, we would mean between negative infinity and 1 and 1 and positive infinity, right? Okay. So number 19, we have a piecewise function f of x equal to the square root of 1 minus x for x less than or equal to 1. Oh, let me check my time here. We're doing okay. We'll do this as the last problem. And x plus 1 for x greater than 1. So we know that this is continuous inside of its domain, and its domain is every value which is positive inside the square root. So if x is less than or equal to 1, then we're going to get nothing but positive values that go into this. So we're okay for x less than or equal to 1. And we know that x plus 1 is a polynomial, and polynomials are continuous everywhere. So so we know that it's also continuous for x greater than 1. So the question becomes, what about at that transition point, right at x equal to 1? Well, let's try to find the limit as x equal to x goes to 1 on the left and the right, and see whether or not they're equal. And as it turns out, they are not. So if I want to find the limit as x goes to 1 on the left of f of x, I would use the top function. It has to be limit equal to the limit as x goes to 1 on the left of the square root of x minus 1. 1 minus x, which is equal to, we can use direct substitution on this. So it's the square root of 1 minus 1, which is the square root of 0, which is 0. If we approach on the right, same logic as in some of the previous problems that we had done, and we get to that the limit as x goes to 1 on the right is 2. So the two limits as we approach 1 on the left and the right are not equal, so the limit is not defined. So there's a non-removable discontinuity at x equal to 1. And that's the only place where this function is discontinuous, so therefore we can say that f of x is continuous everywhere else. Okay, so that is up through problem number 19. And we'll do the rest in another video. Let's see here.